Okay, in this video, I'm going to show you how to do the Fluent simulation. I will still use the geometry I created for our last tutorial. So it's a very simple three-layer geometry. Let me see. Oh, what happens here? Okay. So we have one layer of insulation, and then there is an air gap here, and we have water that fills this inner container. So what we are going to simulate is such a situation. Say we put water at 10 degrees Celsius. Okay, let me see. Okay, water at 10 degrees Celsius. Okay, water at 10 degrees Celsius inside this inner container. And we do not precondition the cooler, which means both the insulation and the air, which originally inside this cooler box, are both at the ambient air temperature. Okay, so here the ambient temperature is supposed to be like, I don't know, maybe 30 degrees. Okay, to be extreme, so it's pretty hot, 30 degrees. So initially the insulation and the air gap are both at 30 degrees Celsius. Then this pretty low temperature water, with the container is put inside this cooler. Then the heat transfer begins, right? Obviously, heat is going to transfer from air into this insulation, into this air gap, eventually into water. So because of this heat transfer, the water temperature is going to increase, but at the same time, the air temperature and insulation layer temperature is going to decrease, right? Because of their contact with such a low temperature water. So firstly, you should understand that this whole process is a transient process, which means it's unsteady. All the temperature values are changing with time, right? It's not a steady state. Everything is changing with time. And secondly, you should understand that the heat transfer, in fact, occurs in a few different modes. For example, the heat transfer from the ambient to the outer surface of this cooler, okay, that happens in the form of convection, okay, or more precisely, natural convection, right, which is caused by the air motion, which is due to the buoyancy force experienced by the air particles. Basically, somehow you may find that this container should be a little bit hotter close to the top, and it's colder close to the bottom surface. So because of this temperature difference, air tends to, moves upward, maybe downward. Yeah, okay. Anyways, that's this temperature difference is going to cause an air density difference, and because of that air density difference, the air is going to flow. Okay, because hot air goes up, cold air goes down. Such an effect. And because of this airflow, heat transfer you know, is is made um, is promoted. Yeah, heat transfer becomes greater with such kind of airflows. Okay. Then the same amount of air, well, okay. Then air flows through this insulation layer in the mode of conduction, right? Because this insulation layer is a piece of solid. It does not move. It does not have any flows. So convection cannot exist. Instead, thermal conduction is the major mode of the heat transfer. Then the heat goes across this air gap layer in the form of convection. Then it gets into this water again in the form of convection. Okay, convection inside water. Again, that is because the water temperature is not uniform inside this container. Some places have higher temperature, some places have lower temperature, and different temperatures, give rise to different water densities. And because of that density non-uniformity, the water particles begin to move, right? And that water motion, in fact, kind of accelerates heat transfer. So that is called convection. Okay, with this picture in mind, we should be able to do our simulation. First, I will start Fluent. So Fluent. Okay, make sure you start the 3D version of Fluent. Also turn on double precision. So start. Okay. Then load the mesh file we created last time. Mesh, where's my mesh? Okay, it's somewhere. Okay, I can find it. I believe you also can find yours. Best design color. It's not here. Interesting. Where it is? Okay, H drive. Okay, desktop. Okay, it is here. Okay, I read this mesh file into Fluent. Okay, you can display the geometry. check the mesh quality. It seems just fine, right? Okay. Now we will use pressure-based solver. We will use transient solver, as I have mentioned, right? This is a transient problem. Everything changes with time, so transient. Also, we have to turn on gravity because natural convection is caused by, in part, by gravity. Okay, different density fluid, has different weight, so to speak, because of the existence of gravity, right? So here you have to specify the gravitational acceleration. It is in the y direction, right, which is a vertical direction, and its value is negative 9.81. It's negative because gravitational acceleration points downward, which is in the negative y direction. Okay, then we go ahead to set up those models. Here, first thing is that you have to turn on the energy equation, which means you have to solve the energy equation for temperatures, right? What this software does, in fact, is solving a bunch of differential equations for parameters of interest. For example, what we are really interested in is the temperature distribution, right? How long it takes the water inside the inner cooler to reach, say, a high temperature, because we really want the low temperature inside this inner cooler to be maintained as long as possible, but of course we want to know how long it can maintain that low temperature. So the temperature, in fact, this piece of information can be found by solving the energy equation. Okay, the energy equation, of course, is just a differential equation based on the energy conservation principle. So right click this energy, then click on, then the energy equation is turned on. Okay, we don't need to change anything else here. In fact, the main thing here is to find the temperature distribution, but another equation also has to be solved. That is the momentum equation, or so-called Navier-Stokes equation, right? Which governs, the motion of fluids. So the ambient, the airflow in the air gap, the water flow inside the inner container. Those motion, in fact, are all, solved from the momentum equation, and this equation, in fact, has already been turned on. Okay, you can see here this viscous, in fact, basically refers to those momentum equations and which turbulent model we are using. Okay, here by default we are using SST K omega model, which is pretty much, in my opinion, okay, the best turbulent model you can use. That is not to say, that doesn't mean that the motion, the flow inside the air gap or in the water is turbulent. It's very likely that the motion is not turbulent, at least in the beginning of this process, but using such a turbulent model, in fact, should be fine, because my impression is that if the flow is laminar, not turbulent, then this model is still able to treat it as laminar flow. Okay, so it will switch to turbulent when the flow really becomes turbulent. So is pretty good. The materials. Okay, you can see that by default, Fluent uses air as the fluid material and aluminum as the material for any solid parts of your geometry. So here we will need to add a few more materials, right? We need liquid water, we need the material for this insulation foam. So right click fluid and click new, then Fluent database, then goes to the bottom of this drop list and select water liquid, copy, close. Okay, let me see if I have that. Okay, water liquid. Okay, very good. Close. So now I have both air, water liquid, and solid. And right click solid and new. Okay, basically you cannot find that specific, foam properties in the Fluent database. Okay, so you have to make your own material. So change the name from aluminum to something else. For example, insulation. And obviously its chemical formula is no longer Al. That is a formula for aluminum. It's a piece of solid. Currently you cannot change this thing, but it will automatically change. And okay, I don't know the density of the foam, the specific heat value of the foam, the thermal conductivity of the foam. So let's pretend. Okay, let's pretend the density of the foam is like 800. Okay, just assume that the CP value is this much and conductivity is this much. Well, the thing is really too high, right? It should be much smaller, but I don't know how small it is. And anyways, let's just keep this value here. It's because it's just a tutorial. Okay, I just want to show you the point. You can make the correct changes by yourselves. Okay, then click change create. It will ask you, do you want to overwrite original aluminum material? You said no. Okay. Then now you have two solid materials. Okay, close. Okay, but that is not good enough. And the reason is because, as I have mentioned, the reason why we have natural convection in the air gap in water is because the densities of the fluids change with temperature, right? So you should allow the density of those fluids to change. Right now, if you double click these two materials like air, for example air, you can see what we are using is a constant density air, which definitely is not going to give us any natural convection. So here you want to change this density from constant to incompressible ideal gas. Okay, using ideal gas, incompressible ideal gas, and Boussinesq assumption all can give us variable densities. But the simplest option is incompressible ideal gas. Okay, which in fact, according to my experience, works very well for our cooler case. Okay, so by using this option, the ideal gas law is going to be used to calculate the air density. Ideal gas law is pressure equals density and times RT. Okay, so density can be calculated from air pressure and temperature. Here, with using this special so-called incompressible ideal gas law, we always, use a constant pressure. We assume that air pressure doesn't change. Okay, there is a fixed pressure, which in fact is very close to our real situation, right? The air pressure inside the cooler is maintained roughly a constant. At least this is our goal, to maintain a constant pressure, right? So here the pressure is constant, so the air density, which equals pressure divided by RT, now only depends on temperature. So when temperature increases, density drops. When temperature drops, density increases. Okay, so this is what happens here. Okay, click change, then close. Okay, now we also need the liquid water, to have variable densities, right? Which it does not have right now. Okay, again, by default, the water density is set to be a constant. Not because liquid water is not an ideal gas, right? So you cannot use ideal gas, those things. Instead, here we need to use a piecewise linear model for the density. Okay, which means I will use a few data points, and data points of density versus temperature, data points, and then I assume that the density versus temperature relationship is a linear function in between every two such data points. Okay, I have found some data points online. See here, I find such a table of water densities at different temperature values. It's not a perfect table. Okay, you may want to find a different table for our simulations, because this table is too, how to say that, is too coarse in a certain sense. Okay, you can see it goes from 0 directly to 4 degrees, then go to 44.4, then go to 10, then 15.6, 21, 26.7, then 32.2. It's a little bit of coarse for our purpose, but well, it's still okay. Okay, we use this 1, 2, 3, 4, 5, 6, 7, 8 data points. Okay, from 0 degrees to 32.2 degrees. Okay, I'm going to do that. Where are my points? Okay, it's here. Why I didn't see the numbers now. Okay, anyways. Okay, I need a few data points. I have 8 data points. Well, that's a lot. How about I only use 3? Okay. You can add the other points by yourselves. The first point is at 0 degrees. The density is 999.87 kilograms per cubic meters. Okay, notice that the unit used here on this table is not the standard SI unit. So 0 degrees, that is 273.15 Kelvin density value is 999.87. Okay, nice. And the second data point is at 4 degrees and density becomes 1000. Okay, what is that? Why always show up here? Okay, so 4 degrees, that is 277.15 Kelvin. Density is 1000. And the last data point is at 4.4 degrees. It becomes 99999. How about I use 10 degrees? Okay, becomes 999.75. 10 degrees, that is 283.15. It is 999.75. Okay, so it is a quite interesting data set. Okay, the water density in fact reaches its maximum at 4 degrees Celsius, and it drops when the temperature is lower than 4 degrees and or higher than 4 degrees. Okay, anyways, now we have such a piecewise linear, density distribution that Fluent can use to interpolate into those data set to find the density at different temperatures. Okay, did I just okay? Then I will set up, materials for different zones, right? Remember we defined 3 zones when we created the mesh. We have the foam zone, we have the air gap zone, we have the water zone. Right now, the foam zone is treated as, all those zones are treated as fluid zones, which is not correct, right? The foam, in fact, is a piece of solid. So right-click zone foam and type, then choose solid. Okay, you can see now it becomes solid and solid. And the material name by default is insulation, which is correct. So apply and close. Okay, now we have 2 fluid zones, 1 solid zone. For the air gap, let's say type is fluid, which is correct, of course. Okay, then edit. You can see by default the material here is air, which is correct. So close it. Then double click zone water. You can see again by default material is air, which is incorrect. So choose water liquid. This is the correct material. So apply and close. So now we assigned air to this air gap zone, water to this water zone, and insulation to this foam zone. Seems good enough, but not exactly. Okay, so here if you double click this cell zone conditions, you have such a window pops up. Choose zone water, then choose operating conditions. Here in fact you will need to set up the variable density parameters. That is, you need to specify the water density at a so-called operating temperature. Right now this operating temperature is 288.16. That is about 15 degrees Celsius. 15 degrees Celsius. Okay, how about we simply use this value? Okay, 999.07. In fact, you can use a different value, right? Anyways, let's pretend that this is a correct value. Okay, 999.07. Okay, Okay, then boundary conditions. Remember that we defined lots of boundaries, right? Surfaces when we created this geometry. They are all in this grouped in this category called walls. Indeed, they are walls, but anyways, here the point is that you don't really need any boundary conditions for those interfaces. Okay, like the interface between the inner container and the air gap, or the interface between the outer, insulation layer and air gap. They do not really need any boundary conditions. Okay. The default condition for them, in fact, is a coupled wall. That's correct. Okay, you just leave it there, which means its temperature will be solved. Okay, from those energy equations, you will not, specify any temperature to such interfaces. Okay, you do not have known heat flux at those surfaces, so you do not know anything. Okay, instead, the temperature values at such interfaces should be solved. Okay, so you don't need to do anything here. Instead, the outer surface, okay, this surface, its condition has to be specified. Okay, otherwise, you don't have a unique solution to your problem. So here you have to specify the boundary condition here. At the outer surface of this cooler, what we know is that there is convection going on, right? Convection going on here. This convection is between the ambient air, which is at a constant temperature, 30 degrees, to this cooler surface. The cooler surface temperature, in fact, is changing with time. Okay. So you do not know the exact temperature at this surface, so you cannot use that. You also do not know how much heat flux goes into this cooler surface, right? But you do know that there is convection going on here at this outer surface, which is in between this surface and the ambient air, which is here is called free stream. Okay, its temperature is 30 degrees Celsius. That is how many Kelvin? 30. That is 303.15 Kelvin, right? Here you also have to give the heat transfer coefficient, that is the convective heat transfer coefficient or convection coefficient. You have to find such values with some hand calculation, with equations you can find from your heat transfer textbook. Roughly speaking, such convection coefficient is at the magnitude, of 10. But it depends on which surface you are talking about. Okay, the convection coefficient at the top surface typically is different from that along the vertical surface, and is definitely different from the convection coefficient at the bottom surface. So here I didn't distinguish those different surfaces, but in your real simulations you want to distinguish those different surfaces, which means you will want to create more parts in ICEM. Say one part is used for the top surface, and one part is used for all those side surfaces, and one part for the bottom surface, and then you can give different coefficient values to different surfaces. Okay, apply, close. Okay, then initialize. Okay, remember that we know that the water inside this inner container is initially at 10 degrees Celsius, right? And air gap and insulation initially is at 30 degrees Celsius. Such information has to be provided to Fluent, otherwise it doesn't know it, right? How can it know it? It does not have ears, it doesn't hear our conversation, so you have to tell it. So initialize, okay, initialize those parameters like pressure, velocity, those stuff, temperature especially. As I said, most temperature values in this system is at 30 degrees, so I'm going to use 30 degrees, which is 3.15 Kelvin, to initialize all the temperature parameters. But obviously it's not all correct, right? Because the water temperature is not so high. So here you have to patch. Which means for this water zone, its temperature is set at a different value, which is 10 degrees. That is 283.15 Kelvin. So click patch. Then the temperature of the water is set to 10 degrees Celsius. Okay, the rest of the cooler is still at 30 degrees Celsius. Okay, you probably want to double check that you did it right. Okay, the patch works. So to do that, I am going to plot the temperature distribution, okay, across on the cross section of this cooler. This is done here. Okay, graphics. Then I choose contours. I'm going to plot the contours of temperature over one cross section of this cooler. Right now I do not have any cross sections, so I'm going to create a cross section. So click new surface, ISO surface, surface of constant mesh. Okay. X coordinates. Okay, compute. Now it shows that the minimum X coordinate and maximum X coordinate. I'm going to use X coordinate equals 0.5 to define that cross section surface. Okay, click create. Then this surface is created. Okay, it's named X coordinate 5 in fact. Okay, if you create another one, it will be called X coordinate 6, and I have no idea why it is 5. Why? I have no idea. Okay. Anyways, close. Then choose this surface. Then display. Where it is. Okay. In fact, it is displayed, but somehow it is in the wrong orientation, so we didn't see it. So press the middle button and rotates. Okay. Now you see it. Now you can see that the temperature, in fact, is correct. Right? And we have 30 degrees here, and we have 10 degrees inside the inner container. Okay, now we are ready to do the simulation. So run calculation. Number of time steps, I will only run 10 steps, and each step is 1 second. Okay, so I will calculate, a temperature distribution 1 second after this initial condition, then at 2 seconds after this initial condition, so on and so forth, until like 10 seconds after the initial condition. Okay, click calculate. Then it's a pretty happy time because Fluent is doing its job and you have nothing to do. So you can relax. You can turn on some YouTube video, although I do not suggest you to do that. But anyways, it is doing its calculations. It's not very stable at first, okay, because of the nature of the turbulent model we use. But it will become better and better, okay. Soon you may find that this so-called turbulent viscosity limited to blah 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 disappears. Okay, it has already finished 6 time steps. No, 4 time steps. Yeah, 6 to go. Okay, 5 steps to go. Okay, I'm not saying that, say, 1 second is the perfect number for time step size. Okay, I'm also not saying that 20 iterations is the perfect number for this parameter. You have to play with such setups, okay, to find out the best parameters, which means they give you accurate enough results without using too much time to do the simulation. You know, you have a really good balance between, accuracy and efficiency. Okay, calculation completes. Okay, let's go back to this temperature contour. Okay, now you can see some changes, right? Although I'm not sure it's correct. Maybe it's correct. Hard to tell, in fact. But anyways, you can see the temperature is no longer, 30 degrees Celsius everywhere except the water, right? The air gap definitely, its temperature drops, okay? And also the temperature is no longer uniform, right? It's different temperature at different places, okay? So if you keep doing such simulation, keep running the simulation, here you can click calculate again. It will continue the simulation, okay? It's not going to start all over again, okay? It will continue simulation from here. Then eventually you can run the simulation for like a few hours of real time, okay? And then you can see how the temperature distribution looks like. What is the water temperature, say, after 3 hours. Okay, so this is the tutorial.